Hi, welcome to this webinar on machine learning classification algorithms. My name is Vivek Singhal. I am a co-founder and chief data scientist at Cellstrat. Just a plug on our startup Cellstrat. We are a leading AI startup in India, based out of Bengaluru, India, and we are working on multiple machine learning innovations and deep learning innovations for selected industry solutions. We produce a lot of research and content in this space, some of which you'll find on our website. We are considered a thought leader in our own right on social media and AI communities. So we are interacting with global top data scientists from across the world, discussing innovations in AI and machine learning. Let's keep going here. Okay, just a brief intro about myself. Well, I guess it's not so brief here. So I am a data scientist myself. I'm the co-founder at Selfstrat, and I have 16 years experience in the US working for companies like AT&T and Schlumberger. I returned to India a few years back, and I worked with IBM in Bengaluru for 2 years. And last couple of years, I have been running a couple of startups. Cellstrat is my most recent startup dealing with artificial intelligence and machine learning. I have a engineering degree as well as an MBA, and we have produced more than 1,000 small form research publications, which you can find on our research blog, some of it. And we are working on multiple AI solutions in regression, predictive analytics, NLP, computer vision, time series, etc. We are also trainers and consultants. We train the global folks who are interested in data science learnings. Let's continue. Okay, so let me come to the topic of the day, which is machine learning and this various classification algorithms. But first, let me introduce you the high-level overall list of data science and machine learning algorithms. So data science is the use of statistical methods to find patterns in data. Okay, so basically it's a science where we are trying to find patterns in data using statistical modeling techniques. And machine learning uses the same maths as data science. So machine learning is sometimes interchangeably used with the word data science. And machine learning uses certain algorithms that get better on their own or that get trained over time with data. So they are interrelated areas. Sometimes we use them interchangeably. And machine learning is the technique by which we train artificial intelligence. Okay, so machine learning is a set of algorithms which help us train AI or artificial intelligence, which are used in AI systems, robots, driverless cars, and so on. Okay, so the list here identifies the major categories of machine learning or data science algorithms, if you will. And one of them is we are trying to classify stuff. We are trying to classify things into category A, category B, or category C, right? So we are trying to classify data samples into three categories, A, B, or C. That's called classification or categorization. The second is we are trying to do a line fit or trend analysis. So we are given certain data samples. For example, these are my data samples on an XY chart, and I'm trying to find a line fit which satisfies most of these data samples. So this is what is we call as trend analysis. And anomaly detection simply refers to finding odd man out. So if my data is following a line here, but there is one poor sample line here, so this is considered an anomaly. And that's what we are trying to do on anomaly detection, because it is not following my usual pattern, right? That's anomaly detection. So I'm just giving a high level overview of all the major, data science algorithms. And how data is organized is about clustering. So this is unsupervised learning, as you some of you might know. We are given a set of data points, and we are trying to find clusters. Right? We are trying to find groups. We are saying, well, this is cluster number one. This is cluster. For example, trying to find, suspicious people in a set of population. right? So we are trying to find clusters of good population and folks with malintention, if you will. And then deciding on future action is coming. We use a rewards-based learning technique to train robots, driverless cars, and also video games. Okay, so this is a newer set of algorithms which we refer to as reinforcement learning or rewards-based learning. So which is trend analysis, anomaly detection, how data is organized, which is unsupervised learning clustering, and reinforcement learning. Okay, so these are some of the major high-level, data science algorithms. So today, our focus area is on classification or categorization. All right, this is our focus area for today. Let me change the color of this pen. I don't like this color. Perhaps I will use red. Yeah, maybe blue and red goes better. How about that? Okay, let me continue here. So if you have any questions, you can feel free to ask them through the questions window, and I'll address them at a suitable time in between the session. Okay. So I see some more folks have joined since then. Welcome to this session. Today we are discussing classification algorithms, which form a major category of machine learning algorithms. Let's continue here. So now let's look at some of the most popular classification algorithms. Okay. Okay, so in classification, we are trying to answer a question whether a data sample belongs to class A or class B, right? Class A or class B. For example, should the bank give a loan to a customer, yes or no, right? So when you go to a bank for a car loan or a housing loan, the bank has to take a decision whether they should issue a, a, a loan to you, yes or no. Okay. All right, somebody is saying I need to increase my volume, which I'll do so. Just a moment, please. I hope this is better. I increased volume on my computer. Okay. So basically, we are trying to classify a bank customer into a good credit customer or bad credit customer, so we can decide whether we want to give a loan to a bank customer, yes or no. How about email? So when we get email, we get a lot of spam. We also get a lot of spam in our SMS, right? Or even our WhatsApp nowadays. So we have to, classify whether an email is a spam or ham, so that if it is spam, the email, gateway can reject spam. It's very hard problem to solve. That's why we continue to get spam till date. Will the kid pass an exam or not, right? So these are all examples of classification, right? I'm trying to put stuff into class number A or into class number B, right? I could have multi-class classification. So here in this visual, you can see that I'm trying to decide if an automobile is an example of a bus, a car, or a truck, right? So it's a three classes are involved. So this is called a multi-class classification, okay? And in case of a bank customer, we may have three different credit classes, whether a bank customer belongs to the high risk class, medium risk class, or low risk class, right? And how about an article? So, if you go to Google News Portal, so Google is syndicating or sourcing a lot of news portals from various news agencies like Times Network or Associated News or one of the other news agencies. And so Google has a task. So Google has a web page on the Google News portal, and it is divided into four sections. So this is political section, this is a sports section of news, this is culture news, and entertainment news. So when a new news article comes into the Google news feed, it has to decide whether this new article, so this is a news article which comes in from one of the news agencies. Should this go to political section, or should it go to sports, or classification, or entertainment news section? I mean, clearly you don't want to see a political news in the entertainment section. You don't want to see a sports news article in the culture section, right? So this kind of correct classification is important. And Google could be using multiple classification algorithms to decide which section of the news portal this new article should be assigned to, right? Another case of multi-class classification, which category this product belongs to. For example, e-commerce companies like Amazon, they would like to classify a new product which got added to their inventory. Is it, let's say, a book? Is it electronics? Is it a mobile phone? So, which category this product belongs to. So, classification is everywhere. Everywhere in our life, in all our businesses, we have need for classification, right? All right, let's continue. So, just a data set I would like to bring up here. So some of you who have operated in machine learning space might be familiar with this data set called the IRIS dataset. So IRIS dataset is a database table with 150 samples. And iris is the name of this flower, okay? Iris is a species of flower and it has four subspecies. Sorry, three subspecies. So it has three subspecies are setosa, okay, versicolor, and virginica. So iris flower comes in three subspecies. Now the question is that so this data set has 150 data samples, and there are four features: sepal length, sepal width, petal length, petal width. So this is a kind of data set which classification model can be trained on. Okay, this is just a sample data set which we can train multiple classification models. It has four input features: x1, x2, x3, x4. Right. So this is the x vector with four features, right? x1 to x4. And this is y. What is y? Y is simply the class label. The class label is whether this is this sample in this row. So each row represents one data sample of that flower, iris flower, whether this particular sample belongs to the setosa subspecies, versicolor, or virginica, right? So this is a data set often used in training machine learning models, often used in machine learning courses and certification programs, and we can use multiple algorithms to train a model which can learn how to classify an iris flower into one of its three subspecies. So there are four input features: sepal length, sepal width, petal width, and one output feature, which is the subspecies of the iris flower. Right? So there are three possible output classes, and the four input features are numerical in value. Right? So sepal is one part of the flower, and petal is the other part of the flower. Okay. So, this is just a botanical data available as a data set, and there are 150 flower samples here, as you can see in this data set. By the way, this data set comes bundled in Python. If you install Python, so Python has a datasets library embedded in it. So this iris is part of that datasets library. You don't even have to download it from the internet. You can use this dataset for all kinds of machine learning training, particularly classification, as well as various kinds of artificial neural networks. Okay, so this is just a data set which provides a good a good data set, good set of data for training various classification models. And the four input columns are referred to as features, as we know, and the output column is the simply the output label. Okay, so five features, four input features, and one output feature. Let's continue here. So, let's look at some classification algorithms. So this is a list of classification algorithms which exist. Some of the most major ones. It's not an exhaustive list, but it is. These are some of the most common ones we like to use. Okay, it doesn't show artificial neural network because we put ANN or neural networks as part of deep learning and not as part of comprehensive or core machine learning. Okay. So there are two kinds of models. There can be linear models. What does linear model mean? Something which finds straight line between two classes of samples, right? So a linear model finds a straight line classifier between two lines, two kinds of data samples. So class A, right? Class B. So this is a linear classifier. However, there could be some kind of data which is all mixed up, right? It's all mixed up. So there are two classes of data samples, but a straight line cannot satisfy a classifier, right? So there are two kinds of data samples, crosses and dots, right? There is no straight line which will satisfy this, right? So in this case, we need to find a nonlinear classifier, right? We need to find a nonlinear classifier means classifier will not follow a straight line, right? So it will be some kind of, so I will create this kind of classifier. So this kind of classifier isolates the dots from the crosses, right? It's a circular logic in there. So these are called non-linear models. So for linear models, we can use logistic regression or support vector machines. For non-linear models, we can use k-nearest neighbors, kernel support vector machines, naive decision tree, or random forest. So these are the names of various popular machine learning algorithms which are used in classification applications. Okay, and there could be two classes, which is binomial classification, or multiple classes, which is multi-class classification. For example, identifying customer segments. For example, low income group, medium income group, high income group. LIG flats, MIG flats, HIG flats, right? In India, we often use this terminology for government apartments, right? A low income group, medium income group, high income group. Or if it is binomial, email, it has two classes. Email is spam or ham, right? And in the image here, you can see I am showing the classification for the iris flower dataset. Okay, so this image shows the classification using most likely either logistic regression or support vector machines. Why I say that? Because the lines are straight lines, right? Lines are straight line. Whenever the lines are straight line, I could be using either logistic regression or SVM. If I was using nonlinear, then it would have found kind of curvature line, right? Curvature line. So if I wanted a nonlinear classifier, the line could look like this, something like this, right? Something like this. It could create a curvature line. So if I create a curvature line, it is a nonlinear model. If I create straight lines, it is a linear model. Okay. And as you remember from the iris flower dataset, there are three classes. So this is the Setosa class, this is a versicolor class, this is a virginica class. All right. So the 150 data samples have been classified into three different class zones, and the fourth, the big dot represents the test data, and I'm trying to slot them into the three classes after having trained the model. By the way, here we are using only two features. So there was sepal length, sepal width, petal length, petal width. But here I choose to use only two features to train my model, just petal length and petal width, just for simplicity purposes, for demonstration purposes. You could technically use all four features, but visualizing a four-dimensional plot on a two-dimensional PowerPoint slide is difficult, right? So visually we can visualize maximum of three dimensions, right? 1, 2, 3. It becomes really hard to visualize a fourth dimension on a paper plot, right? So we have to just extrapolate in our mind and imagine. So normally we simplify things, we operate in two-dimension model, and then we extrapolate in our mind just like we do stuff on two dimensions. We have a third, fourth, and a fifth, and nth dimension. Machine learning models can have n dimensions, which is very hard to visualize. So normally we like to operate in two dimensions and then just extrapolate that in our mind and also in our code. All right. So just for simplicity in this model, we use only two features, petal length and petal width, and we chose to drop the two other features, sepal length and sepal width. Okay, just for simplicity purposes. Okay, let's continue. So now let's look at the first of our algorithms for today, which is the logistic regression. So logistic regression is basically regression. So if you remember, if you attended a regression webinar a few weeks back, you will also find it on our YouTube channel. In the regression, what we are doing, So we have this logic, right? W0 x0, right? W0 x0 plus W1 x1, right? This is your regression equation. And the W's are the weights. And when we say we are training a machine learning model, what we are training is actually uh, we are trying to find ideal weights for this equation. That's what we mean by machine learning. We are trying to find, when we say we are training a machine learning model, we are trying to find ideal weights. And this is a regression equation. So given features x1 and x2, x0 normally we just set it equal to 1. That's it. So x0 is simply 1. So w0 into x0 is simply w0, because x0 is nothing but 1. Okay. So this is in short form. We also write this as you would be aware by now, right? This is vector notation. So in short form, we write the regression equation as vector w dot product vector x, right? So this is vector multiplication, short form version of this expanded equation, right? And so when we say we are doing model training, what we are trying to find is the ideal values of these weights W0, W1, W2. So once we find these weights and we have a trained model, for example, we have an equation is equal to 5 plus 7x1, right? This would be a trained model, let's assume, plus 9x2. There are two input features, x1 and x2, and these three are the weights values which have been discovered by our regression logic. So, and then this is the output level y. So using this trained model, I can predict the future value of y for any new data sample, and given the x1, x2 values of the new data sample, I'll be able to predict the future value of y, right? Future value of a new data sample. Now, so you can see this here. So instead of wx notation, I am now choosing to use the theta into x. Okay. So theta is what? Theta 0, theta 1, theta 2. What is x? X0, x1, x2. This is vector notation. Now you notice this new term here. This is what makes regression different from logistic regression. I am applying the sigmoid activation function. So what is this sigma? Sigma is this S-curve function. What is sigma? It is called an activation function, and it is nothing but an S-curve function. What this does, it converts an arbitrary value on the x-axis into a probability. Okay. So the key point is the sigma or the sigmoid or the S-curve function, as it's called, is converts any arbitrary value into a probability. You can see here the output of this plot, which is the y-axis, ranges from 0 to 1. You may not be able to read it here, but this is simply 0, this is 1. So I convert any arbitrary value on the x-axis into a probability on the y-axis. This is what the sigma accomplishes. The sigma is called the sigmoid function or the S-curve function. Sometimes it is also called the logistic function or logistic sigmoid. What it does, it converts the value of this term theta dot product x into a probability. Okay, so x theta x will be a probability, right? So this is what we are showing. Now, by the way, this is the probability of the output y being 1. And see, probability total always is 1, right? So probability of the output y being 1 plus probability of output y being 0 has to be, total always has to be 1. If you know your probabilities, you understand total of probability is always equal to 1. So what I have done here, I have taken 1 here. So P0 is nothing equal to nothing but 1 minus P of y. So P0 is nothing but, since the total has to be 1, I can find P0 by subtracting P1 from 1, right? So after this equation, I come to this equation, correct? This is what we are showing here. So the first equation represents let me just clear this. The first equation just represents the, the probability of output being a positive, which is y equal to 1. The second equation represents the probability of output being a 0, okay, which is false. So this is true result, this is false result, right? So it's a two-class classification. As you can see here, there are two classes, class number 1, class number 2. So what I'm trying to do through these equations is trying to calculate the probability of a data sample belonging to class number 1, y is equal to 1, or class number 2, right? Let's say this probability is 80%, right? So probability of a particular data sample being positive is 80%. Naturally, the probability of the same sample being a negative is 20%, right? Because total has to be 1, right, or 100%. So this is how logistic regression works, and this is how it varies from regression. So how it varies from regression? We take the regression expression theta vector x and theta dot product x, and we apply the sigmoid logistic activation or sigmoid activation function to calculate the probability of output being 1. And normally, when this probability is greater than 0.5, simply choose to set it output as 1. If this probability is less than 0.5, we set the output as 0. Okay. So ultimately, we want to find the output as 1 or 0, right? So if the probability is 0.5 or more, right, or equal to 0.5 and more, we set the output as 1, y as 1. If the probability is less than 0.5, that means it's a no result, we set the output as 0. All right. This is what logistic regression does for two-class classification or binomial classification. As you can see, there are only two classes here. Now in your mind, you can imagine I can extend this logic to 3 classes or 4 classes or 5 classes. All right. So you have to just extrapolate that in your mind, and we can assume same way we can do 3 class, 4 class, or 5 class, or however many classes classification. Okay. For example, we may have the probability of being classified as sick, whether the person is sick or not, probability of passing an exam, whether the child will pass an exam or not, right? So these are some examples. So probability of winning or losing a match, right? Win or lose. Probability of passing or failing an exam. Probability of health-wise being healthy or sick, right? So these are different examples of where this kind of classification model might be used. And the dependent variable y can only have values 0 and 1, two classes, or I could have more than 2 classes, as I said. And if the probability expression gives me more than 0.5 probability, we set output y as 1, else we set output y as 0. All right. So the solving logistic regression mathematically is slightly more complex than regression. There is no closed form solution, and there is a technique called maximum likelihood estimation, or MLE, which is used to solve logistic regression mathematically. I'm not going to get details of this complex mathematical techniques today. If that requires a longer discussion. All right. Let's just continue here for now. Logistic regression is probably one of the most powerful and one of the most used classification algorithms. Okay. So this slide just shows what we just discussed. That, by the way, so the equation for the sigmoid function. So this is the sigmoid function which we mentioned. Okay. This is the sigmoid function which we mentioned, and this is equal to 1 over 1 plus exponential to the power of minus t. What is t? So t is the value on the x-axis. If you remember, in our case, t was equal to theta dot product x. This was t for us, right? From the previous slide. So 1 divided by 1 plus e to the power of minus t. And that is what, so this value is always between 0 and 1. Okay, it is always between 0 and 1. So this expression will always equate to between 0 and 1, and hence I convert any arbitrary input x into a probability, and this follows the S-curve logic. Now notice certain characteristics of this curve. At very high values of input, this starts becoming equal to 1, right? It saturates here, right? It saturates here. And for very low values of input, it saturates to 0. Okay. So for very high values of input, it saturates to 1, and for very low values of input, it saturates to 0. So the area of interest is this zone. All right. So more than this, mostly it will be close to 1. Less than this, it will be close to 0. So all the play is in this zone, right? This is where things are changing too much. Here, mostly we can say output is 1, very clearly 1, the kid has passed the exam. Here we can say the kid has failed the exam. The question is what happens in this zone? What is the chances the kid passes the exam, right? So this is the area of interest in a sigmoid curve normally. Okay, so that was just a depiction of the sigmoid function. Same thing is here, what we just discussed. So, so this was my sigma, right? The sigma function. Well, this is not sigma function. This is the probability. So this is the probability, and I am applying sigma. I am applying sigma to the theta x vector, right? 1 divided by 1 plus x e to the power of minus t, right? And my what is that t we have? This was theta x vector, right? So what was t? What was t? It was simply the dot product of theta into x, right? And it has to be minus t, as we saw in the formula before, which you see here. And so this is the regression equation. This is the sigmoid function. So this is what is the sigmoid function. Once we apply, we just substitute this expression here, and this is what gives us the probability, right? And in simpler language, we can write this way also. And we already discussed this. The output saturates to 1 as z goes towards infinity. Towards the right, the output saturates to 1, and as z goes towards minus infinity, then output saturates to 0, right? So for very high values of input z here on x-axis, the output can be classified as 1. For very low values of input z, the output can be classified as 0. The area of interest means this, right? We already discussed this. Let me continue here. So that was logistic regression. Okay. Now let me come to the second algorithm for today, which we refer to as k nearest neighbors. Okay. That is the second major or most popular classification technique. We call it as KNN or k nearest neighbor. All right. Here, what we do, we assign a data point to clusters based on similarity measurement. All right, similarity measurement. So let me show on the next slide how this works, so that will make it clear. Okay, so let's see this visual here. So you can see I have a model which has three classes: the green plus sign, the red minus signs, and the blue triangles, right? So this is a new sample which comes into my system, which is question mark. I don't know its class yet, but I check the nearest 5 points. The nearest 5 points. So the 5 is important. Here we have chosen k. K nearest neighbor has a letter k, and here I have chosen k is equal to 5. So I am trying to find the 5 nearest points. And it so happens among the 5 nearest points, 3 of them are the blue triangles. One is minus a red sign, and one is green plus sign, right? So what I do, I simply classify this question mark, this new sample, as blue triangle. Why? Because it's majority vote. Of the 5 samples, 3 are the blue signs, the blue triangles. So I just say, well, it's most likely that this new data sample belongs to the blue triangle class. Okay, so this gets sorted to the blue triangle class by majority vote, and the majority is done on the k nearest neighbor. So that's where the term comes from, k nearest neighbor. So in this case, I am looking for 5 nearest neighbors, and I find that the blue triangle is the best way of classifying this new sample. All right, because it is by a majority vote. So it is mostly in the blue triangle zone, and very less chance of it belonging to the green plus sign or the red minus sign class, right? So this is how k nearest neighbor works. For example, classifying a patient as high risk or low risk patient, or marking email as spam or ham, right? So this is how k nearest neighbor works. Let me just backtrack a little bit here. Go to the previous slide. So I'm assigning a data point to clusters based on similarity measurement. So I'm checking similarity of k nearest samples. So if it belongs, if and I'm doing a majority vote, right? So I have to decide what is k. K equal to 5 is a common rule of thumb. We often use k equal to 5, and then we also have to decide distance matrix. We have to decide what we mean by nearest, right, or proximity. So there are mathematical distance matrices like Euclidean distance, Manhattan distance, and there are other kinds of measuring distance between two data samples. So, so we measure the distance between this data sample and this data sample, and we have different techniques to measure the distance between them, right? And this is what we call as distance matrix. So there are various distance matrices like Euclidean, Manhattan, and many others. You can choose which one we like to use. Typically, we like to use k equal to 5, but it could be an arbitrary number. I could set it to 3, I could set it to 10. It is left to the choice of the data scientist. So k becomes a hyperparameter. If you know machine learning, we have certain parameters which are decided by the data scientist. They are called hyperparameters. Okay, so k is a hyperparameter in the KNN algorithm. All right, I hope that is clear. And so I find k nearest samples, k nearest neighbors of the sample that we want to classify, and we assign the class label by majority vote. Right, in the previous slide, we saw the blue triangle is the majority vote. So the new sample is sorted to the class of the blue triangles. Here, in this visual just shows the iris flower dataset again. So this is the Setosa class, this is a versicolor class, this is a virginica class. And you can see here, KNN is able to find non-linear classifier, right? It has a curvature. It's not simply a straight line, right? So unlike logistic regression, KNN is able to find non-linear classifier. In that sense, KNN can be considered a more powerful algorithm compared to logistic regression because it can do non-linear classification. Okay, at least on that one criteria. Okay, any questions so far? Let me see. What happens if there are equal number of minus, plus, star, etc.? Good question. Let me just go to the next slide and consider that. So let's assume that, so my question mark, is my question mark. This is my test sample, the question mark, and it has, let's say k is equal to 3, right? K is equal to 3. So 3 nearest neighbor. Now 3 nearest neighbor, the one of them is a triangle, the other is a minus sign, the third one is a plus. Our model fails here. So the clear answer is the model failed to find a classification mechanism here. Why the model failed? Because majority vote cannot work because it found one of triangle, one of plus sign, one of minus sign, and assuming k is equal to 3. See, when k is equal to 5, inevitably one of them will dominate. Well, not really. What if this was a minus sign? So there are two minus signs, there's one plus sign, and there are two triangles. What do I do? So one plus sign clearly eliminated, two minus signs, two triangles. What do I do? So model fails here. In this case, the model fails because it is confused whether it is belonging to the minus sign class or the triangle class. Okay. So it may not always work. So in which case you may have to fiddle with the value of k. Let's say your k3 or k5 is giving problem in your testing, then you may have to change the value of k to find a solution to this problem where it is equi-classifying into two or more categories. All right. I hope that answers your question. Any other questions? Okay, so in that case, I would like to open my Jupyter notebook and show you some code samples. It seems people know about this stuff quite well, not getting very many questions, which might indicate people know it very well, which is great. So I'm starting my Jupyter notebook. Those of you who are machine learning developers, we all love our Python notebooks, don't we? So a question came up, if we set k equal to 6 and works for one sample, but other sample may call for other k to avoid tie. So well, yes, so you see it's all about training and testing. So while one sample might work out fine, but the next sample is not able to classify. So well, if it works for most of your test data, we'll probably pass the model. If it fails for most of your test data, so out of 10 test samples, we might say we'll just, if it passes, if it works fine for 8 samples, we'll put it in production, right? So some things will still remain unresolved, but it is able to resolve most of the test cases, all right? So it is just a decision which the project manager or the data scientist has to take, that while it doesn't work for all the samples, but for majority of samples it is working fine, we can pass the model. Is there a way to find k without using default? Well, no, it's a hit and trial activity. So there is, I am not aware of any scientific mechanism of finding the ideal value of k. It's a hit and trial mechanism so far. Okay. Maybe one of the books carries a solution how to find ideal k, but I'm not aware of it. I haven't seen that yet, and it's just a hit and trial as far as I know. All right, let me show you some sample programs in classification. What about grid search? Yes. Well, you're right. You can do a couple of techniques like cross validation. You can do cross validation, you can do grid search, you can do CV search. So there are various mechanisms to discover ideal hyperparameters. You're right. So those of you who don't understand this, there is a mechanism where you run the various you run scores of models, you run many models on a particular data set to find the ideal hyperparameter values. So grid search, CV search, those things can be used indeed, yes. But again, they will be using the data set at hand. When you bring new production data, it could still have a problem. So yes, there is a technique called grid search or CV search which can find ideal hyperparameters. All right, let me show you some simple programs. So let's look at this data set first to understand what data we are dealing with. So I'll show you. Let me show you logistic regression first in the correct order. So let's look at this data set. I'll increase the font size in my Excel file, right? This should be clear enough. So you can see there are two input parameters, age and estimated salary. So this is some person, people data. So the age of the person, 19, 25, whatever, and the salary of the person, right? So $19,000, $20,000, or whatever. Let's assume it's dollars for now. And purchase. So whether they purchase the house, yes or no. So 0 means did not purchase the house, and 1 means purchase the house. So it is two-class classification, also called binomial classification, right? Two classes. So third column represents the Y value, purchase the house or did not purchase the house. Did not purchase is 0, purchased is 1, right? And the person has age and salary provided to us. Can we train a classification model using this data set? Okay. And how many rows are available to us? It's not very big, but we have 400 rows. So minus the header row, 400 data samples are available to us, train our model, right? Let me go to logistic regression. Remember, logistic regression finds a linear classifier. Okay, linear classifier. So I open my IPython notebook and I run this cell by cell. So let me just explain the code briefly. The usual import in Python, NumPy, Matplotlib, Pandas. And then using the Pandas library, I import the CSV file or the Excel file, store it in flat data, Pandas data frame, and the first two columns represented by array index 0 and 1 represent the X vector, right? The the third column represented by array index 2 represents the Y, the output label Y, right? So two input features, the first two columns and the output feature Y, right? Then as you go, since if you are in the session, I hope you understand machine learning process. We usually split the data set into training and test data. And in this case, I'm keeping 75% of the samples for training and 25% of the samples for testing, right? So X train, Y train, X test, Y test, right? So out of 400 samples, 300 are kept in the training data set and 100 are reserved for the test step, right? Then I have to do feature scaling. If you don't understand feature scaling, you should look at our data preparation webinar on our YouTube channel, which discusses the meaning of data pre-processing, data preparation, and within that something called feature scaling, because we are dealing with two features which are on widely different scale. So X, the age goes like 1935, 36, but the salary is a huge, much bigger numerical figure. So we want to scale both those features on a standardized scale so that the larger numerical value of salary will not destroy or damage my model. So this is called feature scaling. I'm using a technique called standardization, and I do a fit and transform on the trained data set. What does fit and transform do? Fit finds the ideal weights for this transformation, and the transform actually transforms it. So first I transform the trained data set, and using the learned weights of the fit here, I also transform the test data set. And I overwrite my X train and X test with the transformed values. Okay, so these two are now overwritten with the transformed values. We don't have to do this for Y, we only do this for the X, the input features only, right? Then I use a library called skikit-learn or scikit-learn, as some people call it, and I use a ready-made API called Logistic Regression, and I create a Logistic Regression instance from this Logistic Regression class and do a fit. What does fit do? Fit finds my ideal weights for the model, right? And using the so fit finds ideal weights, then I do a predict on the test data set. So training was done just with training data set, but testing is done with the X test data set, and I simply am I printing my predictions here, right? And here I print the confusion matrix of what is the correct output values, the known values of Y test, and the predicted values of Y test. So this represents the known values of Y test on the X test data set, and this represents the predicted value of Y test. And as you know, the confusion matrix, the first cell represents true positives, the final cell represents true negative. This is false positive, false negative, right? So to a great extent, it finds the correct true positives, true negatives, and some degree of error. These should have been zero ideally. So there is some error because these two cells are not zero. So it wrongly classifies some positives and some negatives. Okay, if you understand what is a confusion matrix. And then I just plot the output. And the output, since it's logistic regression, you might remember logistic regression does linear classification. It finds this linear classifier. As you can see, some samples are misclassified. So the blue dots are in the red zone and the red dot is in the blue zone, right? So some samples are misclassified, and there is a third axis shown here on the right, which represents the probability of output being a 1. So the right zone represents will buy the house, the left zone represents will not buy the house, right? And this third scale just represents the probability of buying the house. So as I go up in this direction, it represents a higher probability of buying the house. So there is a linear classifier with some error. That's what our model discovered. Here, let me actually run this code in front of you. First, I'll clear the output. Okay, output is cleared. I'll rerun the entire Jupyter notebook right here. It just takes like 10-15 seconds. And so you can see it ran each cell. It printed the predicted output Y test for X test, printed the confusion matrix, and also it plotted the output code. Okay, it plotted the output predictions. It plotted the output predictions. Okay, and here, by the way, you will notice I am just doing this for test. So I am only plotting the test samples which are the 100 samples. Remember, I reserved 25% of the original data set, 400 rows. So about 100 rows were reserved for testing. So I'm only plotting the test samples. I could plot the training samples also in this chart, but so these are total of 100 samples, right, out of 400 samples. And I'm checking whether the classifier correctly classifies the samples into the blue zone or the red zone. There is some degree of error, as you can see, but it is fairly accurate, so we might live with the error. As you know, machine learning is an approximate science. Okay, any questions on this? There's somebody is asking, hi, why I am not able to view the chat details. Yes, I'm sorry. This is a tool called GoToWebinar as you are using. GoToWebinar does not show the chat to the audience. I can only see the questions you are all posing. Audience cannot see the questions. This is how this tool works. So apologies if that bothers you, but this is how this tool works. But normally I tend to repeat the question so you can understand what question was asked. All right. So let me now show you the KNN program. How can we address, there's a question which has come up, how can we address bias variance trade-off? All right. So bias variance trade-off. So as you know, the bias variance trade-off, right? So what is bias? For those of you who don't know bias variance trade-off, what is bias? Bias is the tendency of the model to be near the sample or the average point, right? This is probability distribution of the data set, and the variance is how wide of the data it can cover. Higher the variance, more the overfitting, right? So here I am not calculating bias and variance. The model is probably quite overfitted, right? Here I did not do any kind of generalization. If you notice, those of you who know what is overfitting and regularization, I did not do any regularization, so the model is fairly overfitted. And so variance of this model will be fairly high, bias will be low, right? If I want to reduce the variance or overfitting of this model, I'll have to introduce some kind of regularization technique. All right. Those of you who understand what is overfitting and regularization. Okay. All right. So is the code shared for self-learning purpose? Well, this code is not shared. If you were to take our training programs, we have online certification programs, then we share the code, and we also send you your programming assignment exercises. So not only you get the code in our certification programs, you have to also practice changing the code as per certain requirements. So this code is not shared for webinar audience, but you can find similar code on various GitHub libraries if you were to Google it. You can Google and you can find it on various GitHub libraries. Let me show you the KNN, K nearest neighbors program now. The date. Okay, so the data set remains the same, no change. Okay, data set remains the same. Same two input features, age, estimated salary of the person, and whether the person purchased the house, yes or no, right? So data set is exactly same. Data set is same, only I'm going to use a different algorithm and see if KNN performs better than logistic regression. Okay, let's understand this code. So usual import, then reading the CSV file, importing panda frame, put creating to X and Y data. I'm printing the X and Y data. There are two input columns, age and salary. Output column Y, purchase the house, yes or no. I do the usual training and test data split, 75% reserved for training step and 25% reserved for testing step, right? That's why the 1/4 value there. Then I standardize the two input features on a common scale, feature scaling. Then I'm using the library of Python called skikit-learn or scikit-learn, and I am simply invoking the class k nearest k neighbors classifier, which implements the k nearest neighbors internally. So we are saved from doing the mathematical implementation in Python. The class from scikit-learn does the implements the model internally, and it abstracts the mathematical complexity from us how it calculates internally, right? This is how scikit-learn helps us, sklearn helps us. As you can see here, I'm using number of k as 20. So normally we use k5, but in this case I have put k or number of nearest neighbors as 20. The distance matrix is Minkowski. So I'm using the Minkowski distance, which is the technique how to measure the distance between two data samples on a chart. Yeah, and then I simply call the fit command on this instantiation of the k neighbors classifier API, and I pass the training data x train y train, and then I have a trained model which is inside KNN classifier, and then I predict the output y test on the x test dataset, correct? And I'm just printing the output and input. I print the input test data, then I also print the output, the predicted y test, right? This is the predicted y test, whether the prediction indicates will buy the house or will not buy the house for 100 samples, right? In the test data, we have 100 samples. So these are total of 100 here. Again, I print the confusion matrix. You can see true positive 64, true negatives 29, false positives 4, false negative 9. So 7 samples are misclassified. 4 plus 3, 7 are misclassified by the model. Then again I print the classifier. Again I print the classifier on the plot, a chart. You can see this is KNN logic. So I'm able to do a non-linear classifier, right? Non-linear classifier, and it creates a boundary like this. So just a moment, please. Okay. So non-linear classifier, it creates a non-linear classifier in that measure, right? Non-linear classifier, if you will. So this is with the help of KNN algorithm. So in logistic regression, it found a straight classifier. In KNN, it found a nonlinear classifier. The accuracy is marginally better because you still see some blue dots in the red zone and some red dot in the blue zone, but slightly better because it was able to create a nonlinear classifier boundary, correct? And again, on the third scale, I going upwards, it shows the probability of the output being a +1 or -1. If it is more than 0.5, we usually mark it as +1. If it is less than 0.5, we usually mark it as 0. All right. So any questions on this? Let me just run it for you right here. Meanwhile, you can pose your questions if you have any. Again, I'll clear the output, so it deletes all the outputs from there. All the output is deleted. I rerun the entire Jupyter notebook again. So it's taking some time, but it's running. Takes about 30 seconds probably, or 45 seconds, and it printed the output plot. Yeah, so this is how we run a KNN. We use KNN for a classification model training. Any questions on this? How to decide whether to use linear model or non-linear model? Good question. So whether, see, the okay, let me go back to my slides here to address that one. I would like to take a step back and come here. The question being asked is, which of these algos I should use? Should I use this, which one, right? That is the question being asked. Well, that is just experience of the data scientist. You look at the data set. So data scientists are good at, estimating what algo will do better. But it is at the end of the day a hit and try process. I always test, right, using test data. If my logistic regression model is giving low accuracy, then I might try a SVM. If SVM is also giving low accuracy, I might try a KNN. It's a hit and trial. If you know for sure it's non-linear, you will not even try SVM and logistic regression, right? You will try one of the nonlinear models. If you don't know beforehand looking at the data, then you may try just one by one. It's a pure hit and trial mechanism. There is no specific logic of which algo can be used. Again, you could use grid search or cross validation search. And so what grid search or cross validation search accomplishes, it tries various algorithms in one shot. Okay, so instead of you having to try one by one, grid search or cross validation search will try various models on that data set and automatically recommend which model is giving better accuracy. All right. Sometimes grid search and CV search can recommend the correct algo and the correct set of hyperparameters to you, but not all the time. Sometimes you may have to just do a hit and trial. There is no better way of doing it. All right. Any other questions? Uh, can we test most models and check which is best? Absolutely. You can hit and try all the models and just use the one which comes out to be the best. Okay. Can we use CNN for classification? CNNs are quite useful for images, right? Image classification. Yes, you can use CNNs for classification. They are very useful, particularly for images. But yes, CNNs are used for other kinds of data sets also, not just images. CNNs are convolutional neural networks, very useful for image processing or image classification applications. Next question is, can we use neural nets? Absolutely. So convolutional neural networks or CNNs, artificial neural networks, even RNN or recurrent neural networks can be used for classification. Definitely deep learning or neural networks can be used for classification. How do we use pipeline in stacking the different stages of the model? So pipeline is nothing but an API. Okay. So there is a command in scikit-learn called pipeline. Somebody is asking about pipeline. There is a command called pipeline. Okay, and it stacks various things. So you can do scaling, data pre-processing, then you can do the model, let's say logistic regression, then you can do maybe the visualization or something else. So you can stack various operations using a pipeline mechanism of Python. Okay, so that is just a way of combining various algos in one neat piece of code. It is just a coding technique to combine various algos in one set of code instead of writing standardization, logistic regression, and visualization separately. So instead of writing code one after the another, I am using pipeline command to bundle them. That is your pipeline command. How to approach a decision tree problem. So decision tree is a big topic in itself. I will be covering that in a future webinar. All right. By the way, there may be some content. One of our previous webinars on our YouTube channel did cover decision tree. You can check that webinar. I don't have time in this webinar today to cover decision tree. That's a big classification model in itself. All right. So I'm going to not be able to cover decision trees today. They have lots of nuances of their own. Right. Any other questions? Let me just go to the end where I was. Okay, next question is, uh, shouldn't we use ensemble technique, boosting and bagging instead of individual classification algo? See, boosting, bagging, stacking, these are some more algos, okay? So boosting, bagging, stacking, random forest, they belong to a set of algos which are referred to as ensemble learning techniques. We can use boosting, bagging or stacking also, yes. There are some more alternatives to classification and they may do better in some cases. Next question is, do we need to consider the selection of algorithm based on deployment perspective? So there are so many things, right? So I don't think deployment might matter. I'm just thinking about it. Deployment may not make a difference. You can use any algo which you believe is training your model better. So you can try various algos and whichever does better with your test cases or validation testing, you can use that. I don't think deployment architecture will make a difference per se, right? So can we depend only on Python? Absolutely. You can depend only on Python. There's no problem just doing Python and scikit-learn if the data set is simple. Why we bring artificial neural networks? If we find a simple model using decision tree, logistic regression, KNN, SVM is not doing the trick, That's when we bring the horsepower or the firepower of an artificial neural network or deep learning. So deep learning comes into play when simple machine learning fails to find good models. Okay, can we put this training into loop and get better accuracy? Well, you can increase the number of training iterations in a neural network, yes. So here I am not looping. So in the code you didn't see any looping, right? We loop in a neural network. We train the neural network again and again in a loop with multiple iterations. So, but here it just is right away. There is no loop happening here, as you notice. But I could do, I could do ensemble learning, which will be combining multiple, models to try to find a better accurate model. Okay, now in the interest of time, I'll move forward. So we always get few questions about careers in AI and machine learning. Just a few slides here. So, you can follow, you might be a technical person in which you can follow a technical data science track. If you are not a technical person, you can follow AI for managers track. So even non-technical people can become AI specialist or AI consultant. You can continue your career path of a solution consulting, program manager, quality assurance, marketing, or even sales and HR. But you could still become an AI specialist while learning AI for managers. So we do have a course in this sense, AI for managers. We have courses for technical data scientists, and within this, we focus on machine learning and deep learning. We don't focus on big data, Hadoop, Spark, Kafka, Hive, which are also related to data science. Our focus is on artificial intelligence, which includes, machine learning and deep learning. This is the most glamorous area of today's, current times. Within this, there are specialties like predictive analytics, vision, text and natural language processing, robotics and driverless cars, and many others. So our focus area in my company is machine learning and deep learning, and we have excellent training courses in these areas. Let me just show you those courses. So we have a 6-month learning program. So we are starting a deep learning batch on November 13, which you can find on our Meetup page, and you can do our ML course in either in a live class. These are all online courses, and you can do our ML course in a self-learning mode where I'll be sending you videos and programming assignments. I'll be teaching a deep learning class starting on November 13 every Tuesday and Thursday in the evening, India time, 7:30 to 10:30 p.m. The course number 3 is Advanced Neural Network, which I'll start in end of January. Okay, end of January. So this course comes in January, February of 2019. The deep learning is starting in November, will run till December. And the ML batch I just finished, but you can still do our ML course in self-learning mode. And we have excellent training courses in Python, NumPy, Nonlinear Classifier, Bias-Variance, Tradeoff, Imbalance, Logistic Regression, Neighbours, Bias-Variance, Anomaly Detection, Bias-Variance, Yeah, hi, I'm back. I'm so sorry. My Wi-Fi hotspot dropped, so now I have switched my Wi-Fi hotspot. So we'll just finish up where we were. Okay, so I was telling you about our machine learning programs. So we have 3 course series which take 6 months, and we have very intensive courses which I teach and my colleagues teach. We claim we create AI superstars, right? You can find these programs on our meetup page, and also I like to tell you about our exciting new lab facility. So we are now starting our AI lab where experienced deep learning developers can come to our physical location in south of Bangalore and develop some cool applications with us. So we are running a meetup for related to our lab on 6th of October, which is Saturday morning to evening, and we'll be coding generative adversarial networks. Those of you who are already expert in deep learning and neural networks can are welcome to come to our lab, our coding hours meetup on 6th of October, and we'll be hacking GANs and creating some cool applications from morning to evening. You can find the details on our meetup page, and the location is RMG Ecoward near South Bangalore, near Outer Ring Road, Bellandur area. So most welcome those of you who are expert in deep learning development. You'll have to bring your laptop loaded with Python and TensorFlow. This is not a training session. It is not a training session. It is for deep learning developers who are already expert in developing neural networks. Okay. So this is an exciting thing we are starting so that we can develop some world-class disruptive applications together. Okay. So that was the session. Now let me see any final few questions which have come up since then. What is the best way to deal with imbalanced dataset? So we have to do data preparation or data pre-processing step. If the data set is not clean, it is imbalanced, we need to do data preparation or data pre-processing. So you'll often find data scientists spend a lot of time cleaning up the data even before they can run model training. And that's just a fact of life that you need to clean your data before you can do model training. Which algo is best suitable in those cases? So if the data is imbalanced, there are various machine learning algorithms which we can apply. If you are unable to clean the data and pre-process the data to make it balanced, and the data remains imbalanced, then there are various techniques we can apply. There is a technique called oversampling or undersampling, SMOTE. So we can oversample the less represented samples so that our model will be able to account for them. Let's say there are 1000 data samples and only 5 data samples are of one class and 995 995 are of second class. So the first class has only 5 samples, the second class has 995 data samples. So this kind of classification model will pretty much assign everything as the dominant class, right? So what we might do, we might do oversampling of the underrepresented class. So this is one way we can deal with imbalanced data. All right. Any other final questions for today's session? This webinar has been recorded. It will be available on our YouTube channel in next couple of days. And you can also check lots of other webinars we have recorded on our YouTube channel. A very rich set of webinars which you might enjoy and learn from. Any final questions? Okay, I don't see any other questions. So thank you for your time and attention and very intuitive questions. I hope to see you on our next set of webinars, which will coming up next Monday. Thank you. Good night for those of you in India, and have a very good day for the rest of the world.